In this video, let's take a look at the solution of reviews problems 4.6 and 4.7, solving this system of linear differential equations. We have to determine if the origin is a saddle point, a source node, or a sink node, and if the origin is asymptotically stable or unstable. And then we need to solve the initial value problem if this initial condition is given. So to get started, as always, we need to find the eigenvalues and eigenvectors for this matrix A. Again, it's a 2x2 matrix, and so we have a shortcut method for doing so. The trace of the matrix is going to be the sum of the diagonal entries, -1 plus -1, so that's equal to -2. The determinant of A is going to be equal to -1 times -1 minus 2 times -8. So 1 minus -16 works out to be 17. And so the eigenvalues are going to be found by solving r squared minus -2r plus 17 equals 0, or r squared plus 2r plus 17 equals 0. For this one, we'll use the quadratic formula. R is equal to -2 plus or minus square root of 4 minus 4 times 17 is 68 over 2. And this simplifies as -1 plus or minus 4i, because that is the square root of 64, which is a square root of -64, which is 8i. Divided by 2, we get 4i. Okay, so we can determine a couple things right away. The origin is going to be a sink node, because I have a -1 here, and that means that the origin is going to be asymptotically stable. All solutions are going to converge to the origin. Now, to actually find the general solution, we actually have to now find the eigenvector that corresponds to one of these eigenvalues. Ordinarily, we have to find two eigenvectors, but because this is these eigenvalues are a complex conjugate pair, it suffices to find only one of them. So let's find the eigenvector for r is equal to -1 plus 4i. And to do that, we get the shortcut method is b r minus a. The b corresponds to the upper left right corner here, -8. The r is -1 plus 4i minus a, which is -1. And so we get -8 4i. And we can multiply this by any constant multiple. So we'll multiply it by a fourth, and we get -1 2i. So this is a complex eigenvector, not surprisingly. And we can split it up as -2 plus 0i, then 0 plus i. And so the real part will be -2, 0. And then the imaginary part will be 0, 1. All right, and that'll become important. So this is going to be the vector A, not the number A, but the vector A that I use in the formula. This will be the vector B that I use in the formula. And so from this, I have the two solutions. The first solution is going to be that u of t is equal to e to the lambda t times A, the vector A, cosine of mu t, minus b times the sine of mu t. And in this formula, there's my lambda and there's my mu. And so this will be equal to e to the minus t times the vector A, -2, 0, times the cosine of 4t, minus the vector B, 0, 1, times the sine of 4t. And so this will simplify as e to the minus t times -2 cosine 4t, and then negative sine 4t. So that's the first solution, u of t. The second solution will be v of t equals e to the lambda t, a times the sine of mu t, plus b times the cosine of mu t. So that'll be e to the minus t times -2, 0, times sine of mu t, plus, and mu is equal to 4. And b is 0, 1 times the cosine of 4t. And so this is going to be -2 times the sine of 4t plus 0, then 0 plus 1 cosine of 4t. And so I can combine these to get my general solution that x of t is equal to c1 e to the minus t times negative cosine 4t minus sine 4t plus c2 e to the minus t times -2 sine of 4t times cosine of 4t. Okay, now sketching the solutions of these systems where I have complex coefficients or complex eigenvalues is not so easy. I do know they're going to be spirals. In this case, the origin I know to be a sinc node, so the spirals are going to come into the origin. I can see that here because of the e to the minus t terms. As t goes to infinity, both of these are going to go to 0. And while these two terms account for the spiraling. Now, to figure out if the spirals are going to be clockwise or counterclockwise, I can do a quick calculation on the side. So my original matrix was -1, -8, 2, -1. That was the original matrix I started with. Now let's multiply this by something convenient, say 1, 0. When I multiply, I will get -1, 0, then 2 plus 0 there. In other words, it's just going to be the first column. Now, what that means is that at the point 1, 0, the slope of the trajectory is going to have this direction, -1, 2. So -1, 2. So the slope of the trajectory is going to be in this direction. From that, I see that the spirals are going to be coming in counterclockwise in this direction as opposed to this direction. And so the spirals are going to be coming in like this. So that's one sample trajectory. Another sample trajectory might look like this, where they spiral in on top of each other. Now, drawing the spirals accurately is really tough. These are going to be elliptical shapes in general, and knowing what direction the ellipse is in, as well as how much does the compress as we go along, as time progresses, and I should mark the direction of time is going this way. That's really tough. And so I won't worry about those fine details on the exam. Okay, finally, to solve the initial condition, so, if x of plug in 0, if t equals 0, in this case, that's a 1, that's a 1, that's a 0. So I would get c1 times -2, 0, plus c2 times 1. Again, that'll be 0, that'll be 1. So 0, 1. And that's supposed to be equal to the initial place of 1, 5. Now this one is super easy to solve, and we get that C1 is equal to -0.5 and C2 is equal to 5. And so from there, I can find my solution of the initial value problem is going to be 1/2, or sorry, -1/2 e to the minus t times -2 cosine of 4t negative sine 4t plus 5 e to the minus t times -2 sine of 4t cosine of 4t. And I can split this up if I wished. x1 of t will be equal to e to the -t times the cosine of 4t. If I multiply these two together, I get the -1/2 and the -2 cancels. Over here, I'll get -10 e to the minus t sine of 4t. And the second coordinate, multiplying here, I get 1/2 e to the minus t sine of 4t. And multiplying here, I get plus 5 e to the minus t times the cosine of 4t. And so that is the solution for that particular initial value problem. And this can be graphed using technology.